Okay, so last week when we met, we mainly looked at a few things, and one of the most important things we discussed towards the latter parts of the class was mainly looking at the mass spectrometer. And after looking at the mass spectrometer, we also looked at how the mass spectrum actually help us figure out the abundances of different isotopes in a sample of material. Can you remember that? I told you I will be explaining this part again a little bit today. But can you remember what we did last week? Is that clear? What we did last week, was it clear? You can talk to me. What is the main thing that you found, maybe let's say even a little bit difficult? What was it? Now, since you all are a bit quiet on that front, I will quickly go over the mass spectrum just to remind you of what happens in the mass spectrum. If we take the mass spectrum, we first have this initial understanding that whatever that we include into the mass spectrometer should be a gas. So we take the solid, we include it into a small component of the machine that vaporizes the sample, and then it will be inserted into the mass spectrum. And as these gas particles enter the first chamber, what happens is, first chamber has a electron gun. We call it the filament as well. So the electron gun will be shooting electrons, and if it comes across whatever the atom that you have included, if you take chlorine as an example, this high energy electron will knock out an electron from the atom and then turn it into an ion. It will turn the atom into a positively charged ion. That is what we said last week, right? And this positively charged ion, actually whatever the atom that you include here, it will always turn into a positively charged ion. Majority of the time just +1 charged ion. There is a slight chance of turning into a +2 charged ion as well, but majority of the time +1 charged ions. And then what happens? These ions are going to be attracted towards the charged plates in the mass spectrum, right? Or mass spectrometer actually. There are charged plates like this, and the ion, if I draw the ion a bit small here, the ion Cl1 plus, not minus, this ion will get attracted towards the charged plates. And if it nicely aligns with the hole in the plate or plates, what happens is it will pass nicely through these holes. Now these plates are negatively charged, so therefore this positively charged ion will get attracted towards this negatively charged plates. So because of that, it will get accelerated, and if it nicely aligns with these holes, it will pass through. So these plates are usually there to accelerate the positively charged ion. Is that clear? So, and then it will pass through to the next compartment. In the next compartment, there is going to be a magnet, actually magnet above and below. So we have a magnetic field. In that magnetic field, these particles, they get deflected, right? Based on the type of chlorine 1+ ion, the deflection will change. Lighter chlorine isotopes are going to be deflecting more. Heavier chlorine isotopes are going to be deflecting less. Heavier ones deflect less, lighter ones deflect more, right? So because of that, these, let's say this is how it deflects, and here we have a detector, let's say. So the detector will detect that two places of the detector is getting stimulated. So then, based on how many times that particular location gets stimulated, the detector will produce a graph. This is a computerized graph, in the sense this, whatever the data that is collected over here is computerized. And then, now for example, imagine there is this detector plate, right? And then you have these particles coming and colliding in this, on this detector plate. But they always collide either to this location or to this location, right? So the computer will gather data. It will gather, okay, this location, let's say location A, it got stimulated this amount of times. This location B, it got stimulated this amount of times, right? And then they will turn it into a percentage or level of intensity, okay? And then they will plot it on a graph. So for chlorine, now we'll write the, first of all, the name the axis, intensity here, mass over charge, right? This is 35, this is 37. So for chlorine, there's going to be only 2 peaks produced, and these 2 peaks are going to be like this. These are going to be the heights. Is that clear? Now when you observe from afar, or not from afar, when you observe these peaks, you will see that the peak at 35 is 3 times more taller compared to peak at 37. This is a very important observation, because this is what will lead or allow us to calculate the percentage abundance of 35 isotope and 37 isotope. That's where we stopped the lesson last week, right? I even actually calculated the percentages as well. Is that understood? Right? So then I told you that when it comes to this peak, let's say this peak is 3x tall, right? Imagine the height of this peak right now is 3x, and the height of this peak, let's say, is x, right? So then we can say, if you take chlorine 35 to chlorine 37, abundance means how much of each is usually present in a sample. You can very clearly see the abundance ratio here. So since the chlorine 35 peak is 3 times taller than chlorine 37 height, we can just write the abundance ratio is 3:1. You can express this as fractions as well. So 3:1, if you express this as fractions, it will be 4/3 to 1/4. 4/3, if you turn it into a percentage, it will be 75%. 1/4 will be 25%. Is that understood? So that would mean, if you take any chlorine atom sample, if you just randomly go and get a bunch of chlorine atoms, 75% of those chlorine atoms are chlorine 35 isotope. 25 is going to be chlorine 37 isotope, the heavier one. Is that clear? Understood now? Alright, so we will take a small diagram as well as a small note down. The last time we finished the class, when we finished the class, the last note was about the mass spectrometer, right? So please write a new heading. Please write a new heading. Analysis, new heading, analysis of the mass spectrum. Analysis of the mass spectrum. Okay. Under that, please take this graph very clearly. This is mass to charge ratio, and this is intensity. Sometimes also given as abundance. We sometimes give it as abundance as well. Write these down. Is right. By analyzing the mass spectrum, this is referred to as a mass spectrum. By analyzing the mass spectrum, we can obtain the following details. As somewhat of a subtopic, please write. Not a subtopic per se, so on a separate rule, right? When a specific element sample, when a specific element sample is inserted to the mass spectrometer, then write semicolon, spectrometer semicolon, then write 1. So this is what I'm asking you, mass spectrometer semicolon and then 1. Number of peaks produced, number of peaks produced, communicates the number of isotopes that were present in the sample. To the same point, after that, write example. You can write in the above mass spectrum, in the above mass spectrum, there are only 2 peaks when a chlorine atom sample was analyzed. So please highlight the word chlorine atom, because if chlorine molecules were analyzed, this is a different story. So please highlight chlorine atom sample. Right? And then you can highlight, this means there are 2 chlorine isotopes present in the sample. This means there are 2 chlorine isotopes present in the sample. Okay? Then the second point. So number 2 here. The ratio between the heights of the peaks can be used to determine their abundance. So as an example, you can write this as an example, you can write that. Please write 3x as well. Right. So those are the two main things you can obtain from the mass spectrum. Is that clear? Right. So now write down a small question. A sample of neon gas was analyzed with the use of a mass spectrometer. Based on the information below, answer the following questions. Right. So copy this down. Question number 1. How many isotopes were present in this sample? Identify them. Calculate their abundance. Those are the two questions. Do them. Now, since you can't use a ruler to measure the heights, I have given you the heights. This is 8 millimeters. This is 72 millimeters, right? I will erase that part because that part is not needed. This part. We don't need this. Neon is Ne. You should know its atomic number. What is the atomic number of neon? Anyone? Atomic number? Yeah, correct. Are you done? Can I see? Very good. Yeah. Right. Anyone who's done? Sorry. Correct. Good. Correct. Yes. Done. It's a simple question. Convert into a percentage if possible. Have you? Right. So yeah, you can get to the ratio and then communicate the answer in as a percentage value. Okay. Right. Shall we discuss this? Now this is not that difficult, but I would write the answer here. Now first of all, I specifically told you that this is a neon gas sample, so we know there's nothing other than neon here, and there are two isotopes at 20 and 22. Now students, in reality there are three isotopes, but the 21 isotopes abundance is like very small. It's about 0.26%. So I didn't include that because then it will be difficult for you to calculate. I just wanted to see whether you have now developed the skill to analyze this and get to the answer. Okay, so how many isotopes are there? There are two. One is neon 1020, the other one is neon 1022. So first of all, you have to mention there are only two isotopes because there are only two peaks here, and then you can go ahead with this. And then we have to write the ratio, neon 22. So you can see the first one is 72 millimeters in height, the next one is 8 millimeters. So if you take the ratio between them, it is 9:1. 9:1 means 9 over 10 here and 1 over 10, indicating that this is 90% abundance and this is 10% abundant. Now is that difficult? Hopefully not. Hopefully not. Right. So when it comes to many different elements also students, you have the same story. You have different abundances and you will draw graphs like this. Sometimes they ask you to draw a rough graph of what you expect as well. So you should be able to do those things, right? So we will move forward towards those kind of questions later on. So is everyone okay with this theory part? Anyone who has a problem or any doubt that they would like to clarify? All clear? Yeah? Oh good. Okay, good. Guys, now I think we are meeting for about the third, fourth time, right? You are still bit rigid. Don't, right? If you have something, you can talk to me. And plus, now you are going to hopefully see my face for another year or two, right? So you can't stay like that the entire 2 years. So talk to me and let me know if you have any doubts. Okay? All right. So now we move on to the next part. Now we have spoken about isotopes. We have to learn a little bit about relative atomic mass. We are coming back to isotopes after that, but we have to talk a little bit about relative atomic mass. Now hold on to this theory part because right after relative atomic mass we are coming back here. Okay? Now, when it comes to relative atomic mass students, basically there is a small story that I would like to say and get over with, because otherwise you would wonder why in the world we have another unit for relative atomic mass. Now when it comes to relative atomic mass, the main reason why we started using a relative atomic mass is because if you take an atom, an individual atom has extremely small mass, which is very difficult. Imagine now, when it comes to hydrogen, it could be some 1 point some decimal place values, long number of decimal place values into 10 to the power minus 1920s, right? So extremely small number. Then for helium you have to remember another similar number, right? For what do you call it, hydrogen, lithium, beryllium, boron, all of these, you have to remember all of these different very lengthy, very complex numbers without them being very round, right? So when working with atoms, when we are trying to compare their properties and all of that, it is easier if we have a specific unit that we can use to compare their masses against and communicate a specific mass, right? So what we did back in the day was, we took the lightest element, hydrogen, and compared the mass of hydrogen with other elements. Now imagine, what we did was, we took one hydrogen atom, let's say this is a hydrogen atom, right? We took the mass of hydrogen atom as a unit, equals 1 AMU. A stands for atomic mass unit, AMU stands for atomic mass unit. So we took hydrogen as the atomic mass unit. Is that clear? And then we compared the other atoms' masses against hydrogen's mass and communicated the relative atomic mass of other atoms. For example, if you take helium, helium atom's mass was compared against hydrogen atom's mass, and then realize, okay, helium is heavier. Actually, how many times? 4 times heavier, right? So that means if you have a balance of some sort, if you put one helium atom on this side, you have to put 4 hydrogen atoms here for it to balance. Of course, there was no balance measuring atoms, right? I'm just trying to say, state a point here. So compared to the mass of helium, or compared to the mass of hydrogen, helium was 4 times heavier. So we communicated the mass of helium as relative atomic mass of helium. Helium's AR was 4 AMU. Why? Because helium atom was 4 times heavier than hydrogen atom. So therefore, relative atomic mass, relative mean compared to hydrogen's atom, the relative atomic mass was 4. Is that clear? But then again, I think I told you this story last week as well. So after the discovery of the mass spectrum, we stopped using hydrogen atom's mass as the unit, right? Because there were 3 hydrogen isotopes, hydrogen 1, hydrogen 2 and hydrogen 3. So we stopped using hydrogen atom as a unit because there are 3 different isotopes of hydrogen. We call this protium, we call this deuterium, hydrogen 2, right? And then we have hydrogen 3, we call it tritium. So there are 3 different isotopes of hydrogen. So when we just simply say we are taking hydrogen atoms mass and comparing it against other atoms, then someone could ask, which hydrogen atom are you talking about? There are 3 isotopes of hydrogen, right? So then we had the need to specify and say, okay, this one, right? So before specifying and saying, okay, this one is the one that we are using as the unit, scientists got together and agreed on a new convention. That is, we are going to find a new unit for atomic mass unit. They said hydrogen used as the atomic mass unit seems a bit too simple, too thoughtless. So now they thought we are going to be using a better unit, and that better unit was carbon 12 isotope, which had a mass of 12, right? So we took carbon 12 isotope and we took 1/12 the mass of this carbon 12 isotope as the atomic mass unit. Is that clear? So then we started comparing this 1/12 the mass of carbon 12 isotope against other atoms and communicated the atomic mass unit, atomic mass value, right? So relative atomic mass values are basically obtained by comparing a particular atom's mass against 1/12 the mass of carbon 12 isotope. So if you say oxygen is 16 AMU, that means relative atomic mass of oxygen is 16. So how did we get it? We took one oxygen atom, we took 1/12 the mass of carbon 12 isotope and compared their masses. Oxygen atom was 16 times heavier compared to 1/12 the mass of carbon 12 isotope. Is that clear? So therefore we communicated, okay, relative atomic mass of oxygen is 16. Is that clear? Right. So you might have seen, if you take the periodic table, students, I'm guessing that you use the periodic table. So if you take the periodic table, even in carbon, you have, now when it comes to periodic tables, usually one of the best things to take is chlorine before carbon. I'll take chlorine. Some periodic tables, over here we mentioned the relative atomic mass. So you might see for chlorine the relative atomic mass is 35.5. Has any of you noticed this? Especially when it comes to O-levels at least. Have you noticed chlorine's relative atomic mass is 35.5? Right? Have you? I'm asking for it. Yes? Do a small nod. Yes, we have. Right? So what does that mean? Does that mean chlorine has a new isotope that has a relative atomic mass of 35.5? No. That means, students, this particular value for chlorine's relative atomic mass was obtained by looking at the isotopes that chlorine has. Chlorine has two isotopes, right? One is 35, the other one is 37. If you take any chlorine atom sample, we have both of these. We can't separate one from the other and take. We can, but the thing is, it's going to be extremely difficult, right? So we have, all of these isotopes in any given sample of any element. If they have isotopes, they are all mixed together. Now a fun fact is, if you take water, or if you take hydrogen, actually hydrogen has three different isotopes, right? H1, H2 and H3. Now H2, or the second isotope of hydrogen, which is also referred to as deuterium, now this isotope, right, it is often indicated as D. Okay, now you have H2O, right, water made with hydrogen, normal single proton hydrogen, right? So H2O is something that we always consume. This H2O usually has our normal hydrogen, that is not this particular isotope. Normally, if you take the hydrogens we have, this isotope is the most abundant, right? This one is the most abundant one. It's very difficult to come across these guys, right? This is deuterium, this is tritium. But in certain chemical experiments, we need this D-based water, meaning we need D2O. Okay? A tiny vial of D2O is thousands of dollars in cost. So you can imagine that about 2 milliliters of D2O, not even 2, like the vial is very small, so maybe 1.5, 1 milliliter of D2O is over thousands of dollars. I can't specify value and say, but let's say roughly about $5,000. So you can imagine how expensive that is. Why? Because you have to first of all separate the deuteriums and then move on to react it with oxygen to form D2O, right? So this is a very expensive process. Is that clear? So students, these isotopes can be separated, but they are usually in a given sample present together. Is that clear? So because of that, we can't just put only one isotopes at relative atomic mass here. That will be not accurate because we have a mixture of these two. So we take the average value. We take the average value and write the average. Okay? Any questions by now? You have to have a question now. My God, like, any questions now after seeing this? I said average should be taken, right? we have taken the average. Everything is okay now. Did I make a mistake? What is the problem here? Is it the average? Average between 35 and 37 is how much? 36. But I said this is an average value. I stay corrected, this is average. But what we did take was not just the addition of these two and dividing it by 2. There's something called the weighted average method. So we not only consider their relative isotopic masses, this is actually the mass number, although I pointed to it. For each of the isotope, we can calculate a relative isotopic mass, right? So imagine this has a relative isotopic mass of exactly 35, and this has isotopic mass 37. Now these numbers are mass numbers, these are relative isotopic masses. So now if you are trying to calculate an average when it comes to these types of elements, you have to consider their abundance as well. This is 75% abundant and this is 25% abundant. That means in the sample, the majority of the sample is this light isotope. So when you are taking the average, if you just took these two and then add them together and divide by 2, you are not doing justice. Why? Because most of the sample was this. So the most of the sample was not accurately represented if you just add them together and divide by 2. Clear? So what we do is we take a weighted average. So the weighted average is done this way. I will show that to you here. So we say what we indicate here is average. We say it is average relative atomic mass, right? That is equal to sigma, meaning sum of isotopic masses multiplied by abundance divided by 100. Now for chlorine we can quickly do this calculation, very easy. For chlorine we have two isotopes. One is having a relative isotopic mass of 35 and the abundance of that is going to be 75%, right? So 75%, so 75%, bear with me, 75% could be written like this as a fraction, 75 divided by 100. Now in this expression we have written, we have already taken the 100 denominator, since it's going to be a common denominator, we have already taken it out. So we can just write 75 over here and move on to the next one, right? We have 37 multiplied by 25 and then divided by 100. Now if anyone is curious about how we got to this equation, it's like this. We took 35 multiplied by its abundance, which is 75%. 75% is usually written 75 over 100, right? And to this we have to add the second isotope as well. So that has a mass of 37 multiplied by its abundance 25%. 25% is written like this, 25 divided by 100. So do you see, since these are multiplications, we can draw this line all the way to this area because it's a multiplication. So the numerator and the denominator is very clearly separated like so. And then we can see in both of the terms you have a common denominator. We can take the denominator out. And then at that point you can write 35 multiplied by 75 plus 37 multiplied by 25. So that's how we actually have this equation formulated. But either way, if you just follow the steps, you should get to the answer. So when you solve this, the answer comes perfectly to 35.5. Is that clear? Do you understand this? Right? So this is how you will calculate what is known as the relative or average relative atomic mass of elements. Is that clear? Why do we have a average relative atomic mass? Because some elements have isotopes. So you can't just communicate one relative atomic mass and be done with it. Right? So then you have to consider all of the isotopes and calculate the average relative atomic mass. Is that understood now? Right. Please take a new heading. Average relative atomic mass. Average relative atomic mass. You can write some elements have isotopes. Therefore, when communicating the relative atomic mass, of those elements they are isotopes, those elements comma, then after that they are isotopes, and the abundance of those isotopes should be taken into account. Right. Then write the following equation. Is used when calculating the average relative atomic mass. Only write the relative atomic mass equation that is highlighted here. Just this one, nothing else. And from here onwards, take the rest of the details as a example. No need to take this part down, the rest of it. You can write, when it comes to chlorine, as an example, you can take this down. Once you are done with that, let me know. Once you are done with this, let me know. Done with the example? Have you taken it down? Yeah? Done? Right. Shall we take a small question, because I need to test whether you know how to answer this question. Actually, we have a couple of questions, not just a few, right? So this is the most important part, because when it comes to physical chemistry, from this section of the lesson, the type of questions that can be asked should be that we have to be quite okay with those type of questions. So we are going to come across a couple of questions now, and then we are going to learn how to solve them. Right. So take a new question. Question number 1. Given below is this mass. Given below is the mass spectrum. Given below is the mass spectrum of boron. Mass spectrum of boron. This, right? Then you can write, using the information below, answer the following questions. Right. First question, calculate the percentage abundance of the isotopes of boron second one, calculate the average relative atomic mass of boron. That's it. Those two. Answer those two questions, please. Right. If there is any questions, if you have any doubts, you can talk to me now. While you do the question, raise your hand, I'll be there. Right. Done? What are the answers you have gotten to?
No, almost there. Tiny error. Okay, all right.
Right, good. Can I see? Right. She's got. You are still doing it? Right. Can I see your answers, please?
Right, good.
No, this is. I'm sorry. I think.
This is 32.
Yeah. If it's difficult to see, you can come to the front. It's okay. Right? Sorry. Did you get to?
Yes.
Ali, you have written 52. Okay, all right. Yeah, I have written it a bit small, no? Yeah. Okay. Students, you all can come to the front seats as well. Hopefully, one of these days. Right. So now it's 3.2, not 32. It's 3.2 here, 12.8. So now, first of all, whenever you are given a graph like this, you know what to do. This is nothing new to you. You have to figure out what the isotopes are. So basically, this mass to charge ratio means m divided by z, right? These majority of the time directly communicates the mass number. Here you can write 10 divided by 11. This is actually, when you write 10 here, it's the relative atomic mass. But we know relative atomic mass is awfully close to the mass number, right? So mass to charge ratio, here this means 10, mass is 10. We know when it comes to any ion that is formed in the mass spectrometer, it has a charge of what? Plus 1, right? So therefore charge would have been plus 1. So this is what we usually get as 10 here. Mass to charge ratio 10 means basically 10 divided by plus 1. Is that clear? Right? Now sometimes there are questions asked in certain past papers. You would see there's a tiny peak at 5, like very small one at 5. Now I will cover that part also here. Now they ask, okay, this is boron. Boron has only 2 isotopes. They say that also in the question. Okay, let's say boron has only 2 isotopes. No other isotopes are in the boron. But there is a tiny peak at 1. Tiny peak at 5. Why would we get a tiny peak at 5? Why? Because there is a very small chance of forming a plus 2 charged ion. Do you understand? Then what happens? Then mass to charge ratio becomes 5. Is that clear? If plus 2 charged ions are formed, then there can be a very small peak at 5 and 5.5, because this one also is there, right? Do you understand? So keep in mind, I told you we usually form plus 1 charged ions, but there is a very small rare chance of forming plus 2 charged ions. Then the mass to charge ratio will not directly give you the mass number. Is that clear? Because the charge of the ion is plus 2. The mass is divided by 2 then. Right? But majority of the time charge is plus 1. So that means mass to charge ratio directly communicates the mass of the isotope, which is 10. Boron 10, and the other one is boron 11. Okay? So now what is the ratio? 32 to 120, sorry, 32, not 32, 3.2 to 12.8. 3.2 to 12.8. If you don't like to solve it while keeping it as decimal places, decimal numbers, you can write this as 32, this as 128. This perfectly cancels off, leaving 1 here and 4 here. Okay? So then what is the ratio? 1 over 5, and here 4 over 5. So the ratio is 20% to 80%. Is that clear? You will have gotten to 20, the boron 10 is 20%, boron 11 is 80%. That is your step 1. And then we move on to this equation. We have now calculated the average relative atomic mass. Now average relative atomic mass would be, we have to take the isotopic mass. Isotopic mass is 10 for the first one. Its abundance was 20%. We just calculated here. This is 20% and this is 80%. So this is 20. And the next isotope has a mass of 11 multiplied by its abundance, which is 80%, and then divided by 100. Right? So when you're writing over here, just write the number. Don't worry about the percentage value and the division by 100, because it is built into the equation. Just write the percentage as a number, that's it. Right? So 10 multiplied by 20%, then you write just 20 here. 11 multiplied by 80%, you just write 80 there, and then divide by 100. You are getting to this answer. We have 200 here, and over here we have 880, right, divided by 100. So the answer would be then 1080 divided by 100. 1080 divided by 100 is 10.80, right? 10.80 or 10.8. So what is the average relative atomic mass? 10.8. Right? Now you have many questions like this asked in your papers, sometimes in MCQs also. At that point, we want to sometimes double check whether your answer is correct. There is a tiny, shortcut method to do that. We'll learn about that. So now, imagine this is the mass scale, boron 10, and here boron 11. So let's say this is the isotopic mass. Isotopic mass is 10, isotopic mass is 11. Average relative atomic mass is somewhere here. Right? So now, bear with me. Give me 5 minutes. Right? Now, the average relative atomic mass, we found out it to be 10.8. That is awfully close to 11. Right? Shouldn't it be close to 11? It should, right? Because 11 was the most abundant one. So, since 11 is the most abundant one, it pulls the relative average atomic mass closer to 11. Is that clear? If B was more abundant, this value will be closer to B. However, the answer you get will always be between 10 and 11. It could never be smaller than 10. It could never be greater than 11. If you are getting an answer greater than 11 or smaller than 10, you are wrong. if you are getting an answer, imagine now this one is most abundant, 11 is 80% abundant. If you are getting an answer like 10.08, that means it's very, very close to this one. That means your answer is wrong. Do you understand? Because sometimes your decimal places can go haywire and you might get to a wrong answer. Right? Then double check. Okay, the most abundant one was this. So therefore the average value should be closer to this value. Is that understood now? Yeah, it's a small way of double checking your answer. Right. So as a note, under that answer please write the average relative atomic mass, should always be between the isotopic masses. Then we can write the relative average atomic mass or average relative atomic mass will have a value that is closer to the value of the most abundant isotope. If you want, you can copy this part down, but that is not a must. But this diagrammatically give you an idea about the closeness of the value. So if you want, please take it down. Now, do you understand this part? Good? Right. There are a few more questions I would like to do. After that, we'll move on to the next part. Now I would like to make a simple point a bit more clearer to you. So we have copper, right? Copper has mainly two isotopes, right? We have copper 63 and we have copper 65. And usually if you are doing a question that you come across in certain scientific literature and all that, you would see after writing these isotopes they will give you another value over here that is referred to as relative isotopic mass. Relative isotopic mass. and then we have abundance. So the isotopic mass of copper 62 is somewhere around 62.9296, and the next one is 64.9278. Now then only you start to realize now a mistake that we might have made in the we have made actually. You might have thought that this number and the relative isotopic number is basically always the same. It is not always the same, but they are very, very similar. So in our syllabus we usually don't bother with giving you a separate relative isotopic mass, because they are very similar to one another. Now first understand what this number is. What is this number, students? This is the mass number. It is always a round number. Why is it always a round number? It is the addition of protons plus neutrons. Now this we can't expect it to be a very nice round number. Why? Because we obtain this number by doing what? We compare the mass of this copper atom against 1/12 the mass of carbon 12 isotope, right? And then we try to measure, okay, how many times heavy is this copper 63 isotope. So when you do that, we get to this number 62.9296. This is actual experimental data. Okay, so isn't this, when you round it off, exactly 63, right? Do you understand? Now in our curriculum we don't ever use calculators. No, imagine having to deal with this and another abundance level, like, you know, for example here this is 70% abundant, this is roughly 30% abundant. Now imagine having to multiply this by 70 and then having to multiply this by 30 and then add them together, divide by 100. So it would be a little bit time consuming for you, right? Do you understand? So usually students, in our syllabus the relative isotopic mass is going to be given to you. If they are ever going to be giving it to you, they will give it to you as a rounded off value of this. Basically when you round this off to whole number, it is going to be 63. Is that clear? Now this value is now equal to this value. This is mass number, this is relative isotopic mass. Is that clear? Do you understand? Right? So always keep in mind, this is relative isotopic mass. It has the unit AMU. AMU is a unit that is given for relative atomic masses, relative isotopic masses, relative molecular masses. All of them follow this AMU unit. That's a fake unit. Not fake, we say arbitrary unit. Why? Why do we call the relative atomic mass as an arbitrary unit? If you are just looking at the theory behind it, relative atomic mass is calculated by taking mass of a given atom. In this case, let's say mass of copper 63 atom, the actual mass of copper 63 atom, it's a very, very small mass, divided by 1/12 the mass of carbon 12 atom, isotope atom. Now students, if you take a look at what kind of units are present here, mass of copper atoms should be communicated in grams. Mass of carbon atom, or 1/12 the mass of carbon atom, is also coming in grams. So then what happens? Grams cancel off. So do we have a unit here? No units. So we make up a unit because we don't want it to be having no units. We make up a unit and we communicate that unit as atomic mass unit, AMU. Do you understand? Also now we have, like, you know, new units coming into the picture. One is Daltons. We call Da, right? Actually it's called Daltons, DA, right? Another unit is there, that is U for unit, right? So It's made up units because it doesn't actually have a unit. Is that clear? So sometimes there are MCQs. What are the units for relative atomic mass? So these three are correct for relative atomic mass. Okay. All right. So anyway, just to keep you updated, this is mass number. It's quite different to relative atomic mass or relative isotopic mass. So relative isotopic masses of atoms usually have decimal values, but mass numbers don't. Okay. But to make your life easier when you are calculating things, we round these values off. So actually relative isotopic masses, we give them as rounded off values. I would write it here as 63. I would write this one here as 65. Is that clear? Do you understand now? So at the exam also, if you are given these details, you can basically take the mass number as the relative isotopic mass of each isotope, right? Because they are not going to separately give you like one with a very long decimal place. Is that clear? Right. So now take a new question. After this I'll give you a break. Take a small question because we started I started a few minutes late, students, so I'm gonna. Is there anyone who's having difficulty if I continue the class till 6:15? Let me know, okay? If you have to leave at 6, I will allow you to leave at 6, but I might continue till 6:15 because I started late, okay? Right. Now, write down a question. The below details are about the element copper, element Cu, and its isotopes. Take this down. I will give you the questions later. Okay now, right? Who else is done? Okay, now right, using the information above, that's the first one, okay? That's the first question. Using the information above, draw a rough sketch of the mass spectrum that you expect. Draw a rough sketch of the mass spectrum that you expect. That's the question number 1, right? Now you know the second one, super easy. The second one would be calculate the average relative atomic mass. Calculate the average relative atomic mass. Some of you are done with it. Good. Very good. So now, did you use a ratio of some sort? Okay. 3, 1, 2, 3. Correct. Good.
Can I press 3? Okay, alright. Okay, good. Very good. So now, can I see yours? Small error, right? Your ratios are correct, I think. I'm not sure whether, but which one is more abundant? That one. That one has to be taller.
What is the final answer? Right. Oh, okay. This is correct. Now, when you're drawing the graph, when I say rough sketch, right, just writing the ratios is not going to be sufficient. Right? It has to show, like rough proportionality. Like for example, if this was 2 rules, so if this is 3 rules, this should be 7 rules. If this is 0.3 centimeters, this should be 0.7 centimeters, like that. Okay. So correct that. This is correct. This has the ratio. Did you follow a particular ratio? No, right? But okay, it appears that way. So yeah, maybe correct it a little bit. If you get the ratio, let's say 1 rule higher, same story, right? It's okay. Since it's a rough sketch, we can pass if you haven't properly drawn it to exact proportions. Correct. The graph, can I see the graph? Right. So yeah, correct. So when it comes to drawing these types of graphs, students, more than writing the percentage value on top of the graph, it should represent a rough proportionality. Meaning what? Now you get this is 70 to 30%. So when you're drawing the graph, one thing you have to label the graphs. This is intensity, and this is mass to charge ratio, and over here we have 63. You have to label that. This is 65. So 63 is more abundant. So imagine this is how you drew it. So imagine this was 7 rules high. So I will just write 7x. The other one should be about 3 rules high, so that you can call it the ratio is 7 to 3. Is that understood? Right? So try to keep it to some sort of proportional ratio. If you just draw them like this, it might confuse. Even if you have written 70 and 30 here, it might confuse the reader or whoever who's marking your paper. Okay? Right. So now, so it's the first question you did like that, so no problem. I thought I think you would have learned something from it. So we'll move forward with the next part. Now, let's go to the answer. We have here 63%, so 63 has to multiplied by 70, and we have 65 multiplied by 30, and all of you have gotten to the correct answer, 63.6. Once you solve this, actually there should be a division by 100, right? So once you do that, the final answer should come to 63.6. Right? Anyone who couldn't get to the answer? So all of you have gotten to the answer. Good. Right. So now we'll take a small break. The next one is going to be a bit of a thinking question. I'll give you some time to do that one. But we will start the class after the break. So the question is, there are only two stable isotopes for iridium, and they are iridium 191 and iridium 193. Iridium 193 IR. And then write the average relative atomic mass. The average relative atomic mass is 192.2. 192.2. Now your question is, find the abundances of the two isotopes. That's it. Do this question. All of the information you need are there. Don't look at anything else. Try to do this question now. Right, you can hear me now, right? Right. So now 2H2O. Now students, when it comes to this, did we take grams? Can I say if I take 2 grams of hydrogen, react it with 1 gram of oxygen, I can form 2 grams of H2O? Will that be correct? Will that be correct? No. But we are dealing with number of molecules and atoms. We need to have somehow hydrogen molecular ratio and oxygen molecular ratio as 2:1. But how do we get this? When you are collecting different types of substances or material, the easiest way to measure and get the correct amount is through measuring mass, right? At home also, when it comes to making different things, you measure mass. So for example, baking a cake, right, you measure mass. That's the easiest way to measure the correct amount of substance you need. But here, if you take 2 grams of this and 1 gram of this, does it guarantee we have only 2 molecules of this and only 1 molecule of oxygen? No, right? So therefore, mass directly could not be used when you have this type of ratio given in the equation. If you wanted to quickly get to an answer, if you have about 2 grams, how many grams of oxygen should be taken to react with it? We didn't have a method to get to the answer. Just to clarify students, the problem was when it comes to a mass of an atom was extremely small. Mass of an atom was extremely small, right? This mass was so small compared to, let's say, 1 gram. We could not properly use that mass in day-to-day calculations, easily get to the masses of different reactants we need to react them in the right proportions to get to the final products we want. Now imagine if you don't use the right proportions, one of these two things is going to get wasted, right? Imagine you have 500 molecules of this but 2 molecules of this, then so many molecules of this is getting wasted, right? Because with these 2 molecules there can only be 4 hydrogens reacting. Rest of the 496 molecules are wasted. Do you understand? So they realized, okay, we can't work with these very tiny atomic mass numbers, so we have to come with a value. So different scientists were experimenting with different methods, and eventually one scientist, Avogadro, he thought, okay, if you take, let's say, carbon, let's say the carbon's relative atomic mass was 12, right? Relative atomic mass, AR. AR of carbon was 12 AMU, right? Let's say AR of carbon 12 isotope. So just to be very specific. So he thought, okay, since relative atomic mass of carbon 12, I am going to take exactly 12 grams of carbon, and he calculated the number of atoms in it. Number of atoms. Now the calculation is not that difficult, students. If you know the mass of a single carbon atom, they had the technology to find that. If you know the mass of single carbon atom, we have a whole bunch of carbon atoms, so we know the total mass is 12 grams, and then divide by mass of one carbon atom, right? So then when he did that, he got to this number, 6.02 into 10 to the power 23. Okay, and then okay, it's just a random number. Okay, he just, okay, when it comes to 12 grams of carbon, that many atoms are there. So that was not a very big discovery right now. And then he took another element, let's take sodium, right? So what is the AR of sodium? Sodium's relative atomic mass was 23 AMU. So since the relative atomic mass is 23, he thought, I will match that in grams. And he took 23 grams of sodium. And he calculated how many atoms were present in 23 grams of sodium. And to his surprise, it was this same value. Now he knew this is not just a random number, we are onto something. Is that clear? So when he did try to find the number of atoms in many different elements the same way. So what was his step? He take a look at the element's relative atomic mass. If the relative atomic mass is 23 AMU, he would take 23 grams and calculate the number of atoms of that particular element in that 23 grams. So then he gets to this number. He did this for sodium, he did this for magnesium, he did this for calcium. When he did for many other elements, he got to the same answer. Is that clear? Then he realized, this number is significant, this number is important. So therefore, he communicated his findings and he called this number Avogadro's number, commonly indicated by the symbol L. Sometimes we use Na, Avogadro's number, right? Na or L, both are used for Avogadro's number. Is that clear? Do you understand? So this was how he found it, and he called this number 1 mole. Just like 12 equals dozen, this number equals 1 mole. Is that clear now? Do you understand? Right. So let's take a small note on Avogadro's number. Let's take a small note on Avogadro's number. New topic, Avogadro's number. Okay, right. Avogadro noticed when the relative atomic mass of any element is taken in grams, in that amount of matter, there was 6.022 into 10 to the power 23 many atoms of that element. This number was then referred to as 1 mole. Right. Can you take this down? Starting from there. Now while you take it down, you can listen. Now what is the significance now? Now imagine like one atom of sodium. Imagine this is one atom of sodium, right? Its mass would have been, let's say something like 1.6757. I don't know the exact mass. I can find and tell you, but that is not relevant here. We don't have to memorize the actual masses of individual atoms. But imagine this was the actual mass of a single atom of sodium. 10 to the power, let's say 21 or something like that. This many grams, right? Imagine this was the mass of a single atom of sodium. Now imagine I have given you a total of 46 grams of sodium to you. I ask you, okay, now tell me, without a calculator, I'm asking you, tell me how many atoms are there. Work out. This is the mass of one single atom of sodium. Work out how many atoms of sodium are there in 46 grams of sodium. Can you do it? Can you do the math? No. But now I tell you, in 26 grams of sodium, this many atoms are there, right? And then I tell you, I have given you 46 grams. How many atoms are there? This multiplied by 2. 12.044 into 10 to the power 23 many atoms are there. You can do the math in your head, right? Do you understand the convenience factor here? Right? So that's why we stick with 1 mole, right? So it's a very easy way of working out the correct masses of different elements or different substances for that matter. Is that understood now? Right? If I tell you this is the individual sodium atom's mass, you could work it out with a calculator, right? You will get to the same answer as, let's say, like 12.044 into 10 to the power 23, right? This is not actual value, but if you have been given the actual value, you can do that with the use of a calculator, right? But again, it's a bit more tedious than working out the values directly here. So whenever you take 23 grams of sodium or 46 grams of sodium, you have an idea about how many atoms of sodium are actually there without having to do a calculation with the use of a calculator. Is that understood? So this is a much easier way of determining how many atoms of a particular element is there in a given mass of substance. Understood now, right? Why we stick with this value? Is that clear now? Right? So now at the same time, just like we can go from here to here, we can go in the other direction as well. That means whenever you take 1 mole of any substance, we can figure out how many grams that substance will have. Now for example, let's take carbon. I have given carbon, right? Let's take helium. if I take 1 mole of helium, what would be the mass of 1 mole of helium? You can work it out and tell me. What would be the mass of 1 mole of helium? It will be 4 grams. Why? Helium's relative atomic mass is 4. So if you take helium's relative atomic mass in grams, that is 4 grams. 4 grams have this many atoms, 6.022 into the power 23 many atoms, which is 1 mole. Right? So we can go in the other direction as well. Now if I take 1 mole, what is the mass? 4 grams. Is that clear? Or in other words, if I take 1 mole of carbon, what is the mass of 1 mole of carbon? 12 grams. Right? You should be able to work it out both ways. Is that understood? Right? So please take down this small table as well. That's a tiny table that I would like for you to take down so that this point gets delivered across. Now write a small subheading, molar mass. Write a small subheading, molar mass. Molar mass. And then write a small sentence. Mass of 1 mole of a given substance. Mass of 1 mole of a given substance is referred to as molar mass. Is referred to as molar mass. Okay, right? Its unit is grams per mole. Now per mole means if you take 1 mole, the mass of the substance. Per mole, for a single mole, the mass. Okay, right, example. Right, it's not example, sorry. Right. Molar mass of a substance is equal to the numerical value of relative atomic mass, numerical value of relative atomic mass slash relative molecular mass slash relative formula mass. Numerical value of relative atomic mass slash molecular mass slash formula mass, sorry, there's no period here, in grams per mole. In grams per mole. So after that you can write example, and we have a bunch of examples here. Element relative atomic mass, and here we have molar mass. So we'll start with something like helium. Helium's relative atomic mass is 4 AMU. Molar mass is 4 grams per mole. And then we have, let's say, sodium. This is 23 AMU. So this is 23 grams per mole. We can take calcium, 40 AMU, and this is going to be 40 grams per mole. Molecular mass or formula mass. And here we have molar mass. So the compound, tell me a couple of compounds you like. We'll start with the ones we are most familiar with. This is a molecule, water. We can take carbon dioxide. We'll take sodium chloride. We have to have an ionic compound as well in the mix, right? So all of these are different types of compounds. What is the molecular mass of water? How do you calculate? Hydrogen's relative atomic mass is how much? 1. How many hydrogens are there? 2. So that means this has to be multiplied by 2. How many oxygens are there? 1. So 1 multiplied by, 16 is the relative atomic mass, multiplied by 1 is going to be 16. What is the molecular mass? 18. So this is 18 AMU. So this is the formula mass, or formula mass means basically it's an umbrella term for any compound's mass, right? So formula mass includes molecular mass as well. Formula mass includes molecular mass as well. Molecular mass or formula mass can be used for both molecules, but for compounds you always use formula mass only. Anyway, this is 18 grams per mole, right? We said in the definition, mass of 1 mole of substance, the mass of 1 mole of substance can easily be found out if you take a look at the formula mass and take that numerical value in grams per mole. Carbon dioxide, if you want to see the calculation, I'll do it here. 1 carbon and 2 oxygens, right? Each carbon is 12, right? There are 2 oxygens, oxygen is 16, so therefore 32. When you add them together it is 44. So it is going to be 44 AMU. So this is going to be 44 grams per mole. We will do the sodium chloride one as well for your reference. There is 1 sodium and 1 chlorine. 1 sodium is 23. Chlorine is 35.5. There's only one of it. So 35.5. So 0.5 comes here. 8. Right, 58.5. So this is 58.5 AMU. So this is 58.5 grams per mole. Is that understood now? These workings are not essential. You don't have to write them down if you don't want to. But this part is the example. So example should be there. Is that clear now? Okay. Now students, this is making your life a lot easier than, like, you know, if you had to calculate the number of atoms with the use of the mass, actual mass of the atom of a given element, right? So it's very difficult, that calculation. So this one is making it super easy. Now I'll ask you a question. We know if you take calcium, 1 mole of calcium has a mass of how much? 40. That's why we say 40 grams per mole. A single mole of calcium has a mass of 40 grams. Clear? So if I say I have with me, let's say 80 grams of calcium, how many moles do I have with me? 2 moles. What did you do there? I'm just asking what you did. You knew the total mass, you divided with the mass of a single mole of calcium. Is that clear? So then you got, okay, 80 divided by 40 is 2, right? So we have an equation for that. So we have to learn about that equation before we leave today. So we can easily get to the number of moles of a given substance with the use of this equation. The equation is this: N equals mass divided by molar mass. This is what you did exactly here earlier. I told you I have 80 grams of calcium, and then you immediately divided the 80 grams with a mass of 1 mole of calcium. 1 mole of calcium has a mass of 40 grams. Usually students, what we substitute here is molar mass of calcium. Molar mass has its own unit. What is the molar mass unit? Grams per mole. So we have to substitute the correct unit here. Per mole indicates single mole is 40 grams heavy. Anyway, you can see these cancel off, these cancel off. The answer is 2, and this per mole part, when it comes above the numerator, from the denominator to the numerator, the symbol changes, not symbol, actually sign over here. Minus sign changes to plus. So the answer will become 2 mole. Is that clear? So basically we have now calculated the number of moles of calcium in 80 grams of calcium. Is that understood? Take a new heading. Calculating number of moles. Calculating number of moles in a given mass of substance. Calculating the number of moles in a given mass of substance. Please write this equation down, highlight it. Highlight in the sense, draw a box around it, because it is important. I'll give you only 2 examples and I'll finish the class here. I will not give you questions on this today. Okay. Now, before I move any further, anyone has any questions about any of the parts we have done up to now? Or are you all like 100% clear? Okay? Wow. Good. Like, you know, you all must be very smart. Like, no problems at all. I'm happy. But students, I'm kind of feeling a lack of interaction. So feel free to reach out. Like, this is a small enough class. Feel free to talk to me and like, if you have any doubts, clarify with me. Anyway, we have N here. So please write the meaning of each of these terms. N equals number of moles of a given substance. Number of moles of the given substance. Simple M, not the capital one, simple M. Mass of the given substance. Capital M, molar mass of the substance. Molar mass of the substance. Example. We'll do the example as a question. You don't have to do the question. I will give you the answer. Example. Calculate the number of moles of calcium in 100 grams of calcium. In 100 grams of calcium. So it's done this way. You can use calcium. Usually this is something that I do. If we are talking about calcium, I write calcium and underline it. It is just a preference. It is not like a must. It is something that I do because at the exam, sometimes within a given question, you might have to find number of moles of so many different things. So you have to be clear about what thing you're talking about when you're starting. Now imagine otherwise this n equals m divided by m, there will be so many of them in the same A4 paper or your full scale. And the examiner has to wonder what in the world you have done. Right? But if you have written a topic and then given the answer here, it will be easier for the examiner or anyone who marks your paper to mark your paper. So you can take down this example. 100 grams divided by 40 grams per mole, it becomes 2.5 mole. That is example number 1. Right? Shall we do like example number 2 as a question? I think it's a bit of a challenging one. Not challenging at that much, but let's see. Right? Write down the example number 2. This is not a question, this is an example, but I want you to do it. What is the mass? What is the mass of 5 moles of H2O? What is the mass of 5 moles of H2O? Attempt it, please. 5 moles of H2O. I'll give you 2 minutes. I'll stop the class there after that. Very good. Right. All of you are done? Very good. Didn't take 2 minutes. Good. So first of all, H2O is having a molar mass. We can write molar mass of H2O. This is something that you can get used to. Capital M stands for molar mass. If you write the substance as a subscript, then it means molar mass of H2O. equals 18 grams per mole. Right, I'm just giving you that information here. And then we can just write H2O here, and number of moles is equal to mass divided by molar mass. Now I know the molar mass of H2O. This is done. And they say find the mass for 5 moles. So I know the number of moles. Only thing that I don't know is mass of that amount of moles. So mass is equal to number of moles multiplied by molar mass, isn't it? So we write number of moles is 5 moles multiplied by molar mass, which is 18 grams per mole. We can see nicely mole per mole cancels off, right? So we have when you multiply 5 by 8, it's 40. 40 plus 50 is 90 grams. Okay, so that means when you drink about 90 grams of water, right, 90 grams means 90 milliliters of water, right, you are drinking 5 moles of H2O roughly, because there are other minerals in it, but roughly around 5 moles of H2O you are consuming, right? Do you understand now how many molecules of H2O? Massive amount. Anyway, so if you haven't done that calculation, copy this calculation down, and with this we will conclude today's class. But don't rush to pack things up. If you have any questions, let me know. Any questions? Nothing? Alright, so next week we will be attempting questions from this part, and we are moving on to new theory parts as well. So come prepared. I will, sorry, before you leave, please, especially for the students who are not in the Gampaha WhatsApp group. Students who are not in the Gampaha WhatsApp group, please do this for me. 858-7755. This is my number. Please send me a message saying, please add me to the WhatsApp group, Gampaha WhatsApp group. Don't say just WhatsApp group, Gampaha WhatsApp group 2026. So then I will add you, because I did take your numbers down, but it's a bit difficult for me to type them in, save, and then add you to the group, right? So it's a bit of work. So I don't have the time to do right now. So if you don't mind, please send me a message. Okay? Right. That'll be all for today. I'll be seeing you again on next Wednesday. Alright everyone, have a good night then.